Okay, so for this part 4 of the MATLAB course, we try to go through concepts and examples that were not really included in the software carpentry materials. I try to think of the most common thing that I came across while working with MATLAB, so that most likely you will also come across this same thing. But of course, we're all from different fields, and there might be some specific things that won't be covered. But at least there's lots of resources from the MathWorks website, or other resources that you can find online from GitHub, etc. That hopefully will get you started with whatever task you wish to do with MATLAB. All right. So as I mentioned, I included some examples for today, and I share the code with you. I paste it also in the HackMD code for today and then of course if we see that I'm going to change it, I can update it, but from the link there on HackMD you should be able to access it. But because it's not too I didn't write too many lines, because we understood that speed is better than having too many things. So we can type them together so that you also type them together. So now I do a nice clear all to clean my workspace, close all if I had any window that was open, and even CLC to clear the terminal window here. So I'm gonna do it that on this part of the screen, I'm gonna have the terminal where I'm gonna type interactively the things, and on the right part of the screen, I will have the code that I will copy. I could, of course, run it straight from the editor, but just to make sure that you have time to type it and to understand, we can do it together. Maybe just a little thing. So let's open the first example. Yes, here it is. So we will have an example that uses some data, and we could we could download this data together. So if you go on the code and get this Zenodo link, I paste it also here on the chat for your convenience. So if you click on that link will take you to Zenodo. Zenodo is an amazing service for researchers where basically you are allowed to publish your data. Of course, we are not always allowed to publish our data, especially if you're working with sensitive data, personal data. But often in many fields of science, this is not an issue. So you can actually, publish your data. This specific data set that I'm using for the examples today comes from Kaggle competition. So if you don't know about Kaggle, it's a nice website. It's linked here that you can explore. There's always machine learning competitions and lots of also learning materials and other things if you want to get deeper in computational science and data science. Specifically for this data set, this is just a subset of the full data that is in that competition. The competition, I quickly open it. It was about kind of building a machine learning classifier so that you first train it with actual pictures of cats and dogs, and then there is a kind of test data set to kind of assess the performance. So there is a train data set to train your classifier, and then the test data set. And you see the actual files, they're quite big. There's 25,000 images. So the version that is on Zenodo is just a subset for playing. But you can understand already that by exploring this type of websites, you can find this is an old competition from 7 years ago, but still it's worth checking it for learning, for example. All right, so from Zenodo page, you scroll a little bit down, and there is when Zenodo loads, you scroll a little bit down, and there is a download button. Here it is. So I'm now showing it. So if you click that, it will download a zip with the images. And we all have different operating systems and different ways of unzipping, but basically just unzip the file wherever you want and make sure that with MATLAB you go to a folder so that when you do ls, you see that you have a subfolder called cats_dogs. This is the name of there. So maybe I leave you, few seconds, 1 minute, that you can download the file from Zenodo, unzip it, and make sure that the subfolder is wherever you want to have it. So that in the prompt you see a subfolder called cats and dogs. I can also now, while you do it, I can go inside this subfolder, cats_dogs, and there you should be able to see two subfolders, one for cats and one for dogs. And then if I go inside the cats and do an ls, I see that there are some pictures of cats. So cd ... I go up to the parent folder, and I guess I'm back at the place where I want to be. Now notice that I did a different command because I'm so used to this. These are Linux commands. So ls just lists the files, but here it's a bit difficult to, is this a directory or is this a file? Okay, I know myself that cats_dogs is a directory, but this type of, in Linux, Unix, this type of command, especially the -al, the T stands for time, A stands to show all, and L long version. So if you ever need to work with Linux, Unix, maybe, or Mac, because it's based on the same, then you get these kind of properties for each file. So specifically the cats and dogs, I see that there is a D at the beginning, which means directory. And these are the read, write, and execute permissions for myself, for the people in my group, and for everyone on this computer. But this is beyond MATLAB. I just hope that you manage that if you do ls, you see cats and dogs under your prompt. All right, but let's start first with the first example. So in the software carpentry materials, we've been kind of looking at the data types of MATLAB, and we've been using a lot strings and arrays with numbers, especially double. We also notice other data types like logic data type for those statements. But as I mentioned briefly in one point, there are more complicated, more complex data types. And these are needed when you kind of need to have a data structure that is more, that is not as trivial as a simple table, as a simple matrix. So for example, now I'm showing this link here that you find also in the teaching material. So for example, here they wanna, they basically need to build a database, so-called, they write it element by element organization. So imagine that you are building a database and you want to have name and surname. So if you're familiar with databases, you need records with, in this case, patients. So the first patient has a name and surname, billing, if, well, these are Americans, so they need to bill, thankfully, in Finland. Well, let's not talk about that, but and then some data about whatever, test that this patient went through. And then the same thing for another patient. So to kind of have this, this kind of database record for patient 1 and patient 2, we need to have kind of in the same record, in the same memory location, kind of in the same variable. We want to have a string that is a name, a single number that is a billing, more numbers structure as an array, so we need to have multiple data types, but they all should be kind of contained into the same container. So these are called struct in MATLAB. And now if we do our example here, if we type it together, so now I don't have anything in my workspace. Actually, let's do it clear all. So it's, yes, now I have 0, nothing in my workspace. And now we could, for example, start with the first one. So now I type patient of 1, and I start giving it the name. And the name that we decided is John Doe. All right, so now the struct that I created, the name of the variable is patient, and now it only has one subfield with the name. If you do the whoosh for checking your workspace, you see the name of the variable patient. Now it's just the size of 1 because there's just one element, and it's a struct. Now the class is struct, which is a generic term because there's many structs, and you will come across many structs while you work with Matlab. Now we want to add another field, so it's still the same patient, but now if I would press the tab, it would just give me already name because that's already there. But now we want to have billing, and we want to make it equal to a number, 127. All right. So now the struct is growing. So now we have a struct that contains a string and a number into the same variable kind of. So we are grouping together different things. And then, and this last one I'm gonna copy it. You can copy as well. So then for this patient 1, we want to start adding some data that we need. All right, so now if I type patient, it tells me that this is a struct with the name, billing, and some test, which is a 3x3 doubles. So it's a matrix. Now, what is nice with the Matlab workspace, and I'm gonna make the Matlab window a little bit bigger, and I go with the layout default that you often have. Maybe I still make it bigger and pop out the editor. Now I made this bigger so that we also are able to see this workspace window that you should also have there. Now you see that there is the variable there and there is the struct variable. It's quite convenient you can conveniently double click on the variable patient, and now it opens a new window called the variables window. So now we are exploring the variable patient interactively. And now we see that it's a struct, and now we see, the fields of the struct. So that, for example, I could double click on test, and look, we have kind of an Excel of the data that is actually stored there. And maybe, maybe I could even change one number. I remember that there was an error. Now I have updated the number to 179. And then I can close this variable window that explores the variable. And of course, make sure that things are there. So specifically, this is patient1.test. And yes, now we have the new value here. So using this interactive workspace, you can explore the variables, and it's not, of course, like from the reproducibility, it's not, of course, recommended to, like I did now, manually change values, because maybe nobody will remember that I manually did this. But in practice, if you need this kind of more interactive way of working with Matlab, almost like having an Excel under the hood, then you can do it using this workspace and clicking on the variables. Now let's go back to our simple layout with just a common window. And common window is here. We have to undock the editor. Okay, and make it a little bit smaller. All right, so now we have one patient. So our variable patient just has a single kind of item, a single record, but then we want to add another record. So now I would start typing patient 2.name, and now there's a new name for patient 2, and Lane. All right. So now if I look at patient, now if I just type patient, it tells me that it has, kind of a size of 2. And now we don't see anymore the values because maybe we don't have the values for all of them. So if I type patient of 1, now I see the values for the first patient. If I type patient for 2, now I have empty arrays. So already Matlab, because of the struct, Matlab knows kind of the fields that we should be having there, but right now we have not added anything, so they're the so-called empty arrays. Matlab can't guess if they will be numbers or matrices, single numbers, etc. So then we continue populating our database. So we miss the billing info. Of course, you can press the tab button so that you don't need to type the full string. And this is 28.50. And then for the patient 2, this last I'm going to copy because there's many numbers that I don't want to type. And now we also have the test data. So when I type patient 2, so the second element of this array, struct array, as Matlab writes it here, I see all the data for this. And then patient2.test, I see specifically the subfield test in the struct. All right, so structs are convenient for these purposes, but there's another reason where structs are basically convenient. So another way of using struct is when you need to load multiple files from Matlab. Now, maybe before continuing, I check the HackMD if there's any questions. All right, there's no question. I remind you that the code that I'm using is here. So that if you, it's basically this, and here you see the files. Now I'm using the first one. All right, so we were saying earlier that we managed that I asked you to download this file and unzip it. Hopefully you all have it under your subfolder. And so now in this example, we wanna first create a so-called mat file. So .mat files, so files with the extension mat, they are binary files and they can contain MATLAB variables. They can, of course, contain a single variable if that's all you need to store, or they can even contain the whole workspace. So for example, now if I check my workspace, I see that I have the variable answer because I typed this interactively, and I also have this struct patient. So I could save the workspace and let's call it test workspace. So just by using this, now what will happen is that Matlab will save the whole workspace, meaning these two variables that I have right now in the workspace, into a mat file that will be called test workspace.mat. So let's try this together. Right, now let's do ls. And now I have a variable test workspace.mat. I could then clear my workspace, clear all, even clear the window because it's nice to start fresh. Let's double check my workspace is empty. Now with load test workspace.mat, now I have the variables back again. So this is quite convenient if you know that you're doing interactive work and you need to, you need to switch off your laptop because you need to reboot or you need to log out from your workstation. So you can save kind of everything by just using the command that I used earlier here, save, and just the file name where you want to dump everything. And then it kind of takes a snapshot of your workspace. And it's there for tomorrow to continue again. Of course, you might be having many variables open. And sometimes basically, you don't want to save everything because if you really have many variables open, maybe it will take ages to write everything to disk and it's not convenient. So sometimes we can use save more like we would use a function so that we could specify, for example, which variables we want to save. And this is exactly the example that we're going to do right now. So instead of saving the whole workspace, we want to save only some variables that kind of have a meaning, that they should kind of live together. So in this example, I first create kind of my data by reading an image. I decided for this example because then you know also how to read an image with Matlab. So let's go ahead. So X is the name of our data, image read, and now I have to give the path where this cat image is stored. So we should all have a subfolder core cats underscore docs, and here specifically I want to load from the cats, the cat2.jpg. I put the semicolon at the end because I don't want to see the full X. Now I press enter. So now ImRead is reading an image. As you can guess, there are many something read functions in MATLAB to read audio files, to read videos, to read multiple data types that you might work with. Luckily also, if MATLAB wouldn't have a built-in function to read the specific data type that you work with, most likely somewhere somebody has made a toolbox so that you could read, whatever is the type of data that you work with. Now we check the workspace, and now we have this X, which is the variable, this image that we just loaded into the memory. So it's an image of 396 times 312 pixels, and it has a third dimension. If you are familiar with images, this third dimension, they're so-called Rgb channels, so red, green, and blue. The class, so how these images are stored, it's a different type. It's not this double precision, but it's this unsigned int with 8 bits. So going to the types of how numbers are stored in computers is kind of beyond the scope here. But the idea, as you can kind of guess already, if you're not familiar with this, that we only use 8 bits to store kind of the intensities at each pixel. So now just to make sure that we loaded something that makes sense, we can type image SC, where SC is kind of stands for scale. So it kind of takes care that the image has the right colors, if you want to think it like that. And I just passed this image X. Now we press enter and we see the cat. Now you see that the ratio of this image is a bit weird. The picture looks like a bit squeezed. And if I would start playing with the ratio of the window, it would even get even worse. So this is because MATLAB doesn't really know that this is an image, and kind of the axis, the pixels should have the same length. That if something has a distance of 50 here, of some centimeters or whatever pixels on the screen, it should also be in that same. So then to fix this, we can use the axis command and specifically tell MATLAB, we want the axis to be equal, so that if it's 1 centimeter, if it's 50 pixel in the X direction, it should also be 50 pixel in the Y direction. And now the picture looks like as it should look. Then sometimes when we plot pictures, we don't really need to see all these kind of coordinates, because we might just want to look at the pictures right now. So another command is axis off. So now we just look at the picture, and of course it's always nice to give it a title, our test picture. All right, so I basically used the few commands that came just after. All right, but now if we go back to our example, okay, we created the X, we created the data. My goal here is that we are kind of trying to build we're kind of trying to group together into a single math files all the things that we need for this file. So we need the actual data in math format. We still want to keep kind of track of the name of the picture that we loaded, and also this label, because maybe we are planning to build this machine learning, so that we need to know kind of the ground truth of the image. Is it a cat or is it a dog? So then I'm adding some other fields or variables. cat.2.jpg is the name. And then we also decided to have a label if we're going to plan to do machine learning. All right, so now if I check our workspace, so we have X, that is the data, we have label, and we have name. This is fine. Of course, if we wanted, we could kind of group them all together into a struct, like we did earlier. But maybe often, it might be convenient to have them all separated, because, because this is maybe how the data that they gave it to you, or maybe because that there's another application that should load the data. But this is also for kind of teaching purposes, that we want to now, in our workspace, there are also this patient variable and this ans variable. We don't want to save those. Now we want to just save these 3 variables that are related to this cat image. So now the save command, I use it as a function. And the first parameter will be the output file where I want to save. And then these are all strings, the name of the variables that I'm planning to save. So here you can put as many as you need. In our specific case, we want to store in the mat file cat.mat the three variable x, name, and label. All right, so I press enter. And now I do ls, and you should do the same. And now I see that I have a cat.mat in my folder. Let's clear all and close all, and even clear the, well, maybe I don't need to clear the history if you want to read it. But now we want to do the same for the dog, for one of the dog images. So now for convenience, I'm just gonna, well, maybe I'm gonna type it so that you have also enough time to catch up with the coding. So now I wanna read, IM read, image read. The name of the file is cats_docs/docs/doc.4.jpg. Okay. So now it's loading the image. I check. Now this is a different size. The previous one, you see it here where my mouse is, was 396, 312 pixels. This one is a little bit different because in this data set, kind of, they made things a little bit complicated. They are just kind of random pictures. Some are bigger, some are smaller, some are high quality, some are low quality. The classifier, the machine learning classifier that one should build should kind of, be invariant on the size of the images or the quality. All right, so then we want to also remember the name of the file that we loaded, and in this case it's doc4.jpg, and the label for our machine learning, which for this image is dog. Okay, so yeah, now we're basically ready to save also the dog.mat. So I do the same. Now, before we did for cat.mat, and now we do it for the dog, but it's the same variables and the label. All right, so let's check our workspace. We have these variables. Maybe it's also worth checking, did we really load the right image? So I do again image sc x, and yeah, this time looks like a nice dog. We could also do axis equal, even though this image, yeah, the ratio was almost 1-to-1, and then even switch off the axis because we don't need those numbers in this specific case. And so we have a dog image and it looks good. Now, what I was mentioning earlier, the purpose of doing this is that we have now created two mat files, one that is called cat.mat and the other that is dog.mat, but they were not made as a struct. This is quite often that you get some mat files that you actually have no idea. Sometimes somebody gives you a mat file. Will there be just one variable with a struct, or will there be 100 variables? And then it starts to become problematic because, so let's say that now in my workspace, so we have the dog stuff, we have the X and the label and the name. If I just do load cat.mat and then press check the workspace again, now I have overwritten the stuff that I had in my workspace. So now, I didn't know that my colleague gave me a mat file that had that variable called X that I already had in my workspace. And now there was no warning. I just my X variable that I had here, there was a dog. It got overwritten with the content that was in cat.mat. So this is not good. There was no warning, and I didn't know what was in this cat.mat. So one way is to call the load command with the left, kind of with an output argument. So in this case, we call it data. So if instead of typing load and name of the file, we also specify data equals load, and now we use it as a function. So we want to pass a string with the name of the file. All right. So now we have a struct. Now data is a container, and as a struct, all the stuff that was inside the cat.mat Matlab file with the name of the variable. So the name of the variables became the fields of this struct, and the data, of course, is still there. This is the label is cat, this is the file name, etc. And of course, you might know that now this, of course, this is a simple case that we built ourselves. We know already that the next kind of mat file follows the same structure. But you might have had a script that generated these 100 mat files with the same variables. And here you can do the same thing, so that kind of like we did earlier with the patient. So now we write data of 2, so in the second position of this struct, and now we want to load the dog.mat. And now our array has a length of 2, has 2 elements, and data of 1 as the cat image, which was 396, 312 pixels, and data of 2 as the dog image with a different size. So this is also nice to notice that, we can have kind of each struct is independent from the other. We don't need to have exactly the same number of pixels, for example. So every struct doesn't really matter on the other. All right, so hopefully you were all able to reach this point and type it along. I quickly check if there's any question in HackMD. There are no questions, so we can continue with the third example from this first part. So another very useful thing. So now we looked at structs so that you can kind of group together, kind of database records that one item, like one record, needs to have multiple fields related to that record, like the patient name and billing and test data, or here the image data, the image label, and the image name, file name. There is another type of data structure in Matlab, which is called the cell. So I pasted here, the link that tells you more about cells. But the idea of cells is basically that a cell array is still an array, so it's still a matrix, whether it's a row, a vector, a two-dimensional matrix, three-dimensional or more. But now the difference compared to all the matrices that we've been working with is that all the elements in the matrix, in the array, they don't need to be all of the same type. So it's not kind of a matrix 2 times 2 of numbers, and they all need to be numbers. Here, each location, each cell can be whatever is, the value that we need to store there. So kind of the cell, it's still a matrix, it's still an array, but now we are kind of free to put in every cell whatever we want to put. So now here in this example, for example, in this cell that is created here, in the first row, we have 3 numbers, 1, 2, 3. And in the second row, in the first location, actually, we have a string. Here we have a matrix of size 5 times 10 times 2. It's a volume, actually. And then inside the cell, there is another cell. And this cell also has, some numbers. So I'm not going to type it because I don't want to do mistakes. I'm going to copy paste it and you can do the same. Now, so what you notice the difference compared to the arrays. So if this would be a matrix, I would have written it, my matrix equals square brackets, 1, 2, and 3. And of course, they all need to be the same type. So the second row would be also only numbers. I can't start writing strings or other strange things. So, but for cells, instead of using this square bracket, we use these curly brackets. I hope it's clear that these are curly brackets with the quality, with the video quality. So that by using curly brackets, MATLAB know, all right, you're not defining an array with all the numbers that should be the same type, but you're actually defining a cell. And then these 2 rows, 3 column cell has different types in the first one in the location first row, first column. There's just a number, same and same for the first row. But then here we have a string, and in the locations row number 2, column number 2, we actually have a volume. So this is a volume with 5 rows, so x is 5, y is 10, and the z direction kind of has 2. And then here within the cell, we can even nest other cells. So of course, cells are very flexible, but you can already understand that it's not the most convenient data structure if, you know, if you need to process data. Imagine that you're doing signal processing and you have a time series. You wouldn't store a time series as a cell, because time series, if they're all samples, they're all from the same type, and then the speed, you know, it's obvious that there's more speed by using a simple type like just an array. But the cell might be very, very useful, similar to the struct, so that you can combine different things together. But the difference compared to the struct is that now you have the so-called table format, you know, array format. So that basically, let's say that you know that every row is a patient, and then you can have these variables that the first column is name, and then what was it, billing, and test, and the test data. So it's another format similar to struct, but a little bit different. Then here, because they're structured as an array, because the cell is an array, or cell array as it's called, we can of course get to the location that we want. So notice here that now I also use the curly brackets. So the curly brackets, if I type my cell curly brackets, let's type it, my cell curly brackets, row number 2, column number 1, should be this text. All right, so the answer is text. And if I check the class of what I just typed, it should be basically an array of characters. Yes, so it's a string. But if instead I would have used the round brackets like we normally do with arrays, this is actually a cell. So if I access the content of a cell with the round bracket, it just returns me a cell, which can be useful sometimes, but in this case, it wouldn't be useful if the input of my function doesn't want a cell, it wants a char. If I want to access the actual content that is stored there, then I'm gonna use these curly brackets. And now I get a character string. And then in this specific case, we call the function disp, and disp wants to have a string as an input. And so disp will display the content of the cell in location 2, 1. Cells are also useful to kind of convert between structs, and especially if you know that that things are a little bit more complicated. So for example, in this data struct that we built with our cat and dog images, so the x, they are, oops, now I showed everything. So the x are different. So the x for the first image had the pixel size that is different from the x of the second image. So if I would just type data of x, this is of course, now it's going to show me everything, but basically what it throws, like what this thing does is kind of returning me cells, where it will return first the first cell and the second cell. And they must be cells because they are different sizes. It wouldn't be able this to return, you know, all the two elements of the struct in as an array, because they have different rows and different columns. So basically I could just, with this notation, images equals, and yes, make it sure that it's a cell. So now, oops, I gave it the wrong number, wrong name. So now if I look at the class of the images, it's a cell. And if I type images, now I have kind of extracted the data that was stored in my struct. I only needed the x variable, and now I have a cell array with, you know, in the first location is the first image, and in the second location is the second image. Okay, so this is a good moment for some question. We kind of went, hopefully slowly enough, through the first part that talks about data types and data structure. If you want to write your questions to the ACMD, in the meantime, I still want to show this page from the Matlab documentation. So all these examples are under the language fundamentals data types. And so here, the numeric types and the character and strings were covered in the carpentry, in the software carpentry material. But then there are other data types that we didn't really cover. We cover structures and cells because these are very common and you will encounter them. They are often the output of functions. Often the output is not just a simple numeric matrix or string. Often the outputs of functions are structures or cells. But then there are other data types, like types for time series, for tables, categorical data, dates and time. So, you can explore what you need from this page. I can paste the link to the chat for your convenience. All right, so let's have a look at HackMD. There's no questions, so maybe it's a good moment for a 10 minutes break so that we can resume at 13 o'clock. And for those who want the credit or the certificate or both, please send me a chat message in Zoom with your name and surname so that I mark your presence. And so, yeah, let's have a break until 13. Okay, we can start again. Thanks for those who sent me their name and on a chat message on Zoom so that I can mark your presence for the credit or certificate. Right, before continuing to the next step, and of course, in the meantime, you can always use the HackMD if you have more questions or comments. I repaste the HackMD for your convenience in our Zoom chat. I wanted to show another feature of basically images and explore images. So we had loaded some data. I'm now use the history. So I start typing and then scroll up. So for example, now I'm going to reload the data for the dog. And then we did this. I close everything to make sure there are no figures open. And now I do image SCX. All right, so we did this display. So now my Matlab has a version that is the 2017 version. And this toolbar here at the top is a little bit different. So now I can also from remote use a different version of Matlab that, how can I say, that it's more recent. And I have it in this window. So if you have a more recent version of Matlab, you are able to basically, this would be what you see if you type what I just did, this image SC of this dog picture. So now there are things that I would like to comment on this, basically figure interface. So there are obvious commands or not obvious, but familiar commands like you want to reopen a figure or save it or print it, etc. But then there are useful things, and a very useful one is clicking on this edit. So you can actually interactively work with the data, with the image specifically that you have here, and with the properties of the file. So for example, now that I selected that I switched on this edit plot feature, I could double click on the axis. And there should be an interface, yes, the inspector, property inspector. And so I kind of see here kind of all these properties of the axis that of course we can change programmatically like we did earlier that we wanted to have the axis equal because of the ratio, but we can also change them without typing any code. Kind of, I want to change the font, for example. There is a Matlab code to do that, or I can do this interactively here. Of course, you can already see from the reproducibility point of view, it is better to write it as a code, because then next time you know that you wanted a different font or that you wanted a different axis. But in general, you know, with this tool here, you can explore any property of the figure. Later, this is useful when working with the kind of time series plot. So I will show later how this is, or at least how I normally use it with the time series, also called line plots. And then another thing that if you kind of, now I switch it off, we don't need this edit tool anymore. If I hover over the image, you see that there is this, it's a bit kind of gray on gray, but there is this menu that comes out where we can basically do extra things with the image. So there are these zoom options that, if I click, now I have the zoom tool selected. So I could, let's say, zoom on the, yes. So now I zoomed in into the image. And if I recall correctly, this home should bring it back to the normal view. And then another useful thing is this looks like a, like a little box with some text. It's data tips. So data tips is useful. This is an image and there's lots of data. And maybe I'm not really sure, about this, whatever data that I'm interested, but let's say that I really want to look at what is the value stored here in the eye of this dog in the image. So I click in the location and Matlab tells me, okay, you are at coordinate 198 and 92, and these are the RGB values that are stored there. So kind of this is another interactive way of exploring images. Again, later I will show you how this is also useful for time series and also 3D plots, because some people were wishing for 3D plots. If you have an older version of Matlab, like I have on this other machine here, the kind of properties are the same. It's just that basically in the past they were here, part of the menu. So this data tip would be this, and here it would show me it's a bit tiny. So it's it has improved in the recent Matlab version. All right. So let's quickly check if there's any question or comment in the HackMD. And there's nothing, all clear. So then we can continue with the part 2 of our things for today. So I edit Matlab Basics 2020_4_2. Okay, now I loaded it in the editor. It's good to start fresh. I remind you, because this is a section, you see that it's highlighted. So I can always right click and evaluate, kind of run only the section that I'm running. So evaluate current section. There's even a shortcut for Mac would be this command enter. For some other computers can be F9. It depends on your operating system. But now we clean everything. There's nothing in the workspace. There's no window open. So now we change a little bit of topic. If we kind of mention now about how to store the data and even how to load the data, specifically Matlab data, we also looked at image, how to load an image. Then we often need to do something, some math, some processing of the data that we have in the memory. So now these things that I'm writing here, they are somewhat taken from this link that you see there. I briefly open the page just to show it to you. But basically it's still part of the kind of language fundamentals. And it kind of go through something that in the software material was quickly covered, and here it's I thought that it's useful to spend a little bit more time on this. So we have seen that we can define arrays like with this notation. So often you can have the commas, or you don't need the commas if it's clear, like in this case that it's a space. So let's define A, and it will have 1, 1, 10. And now we see 3 values. Double check it. You can do the same if you, I'm gonna type it so that you also have time to do exactly the same thing. Then we have another row vector B, which contains the value 1, 2, and 3. And then I check my workspace, and yes, they're both double, so double precision digits, and 1 row, 3 columns. All right, so then because these are of the same size, I can do A plus B. So this operation of A plus B will kind of sum, element by element. So if I do A plus B, the result will be the first element in A with the first element in B. And it's correct. If B would have been a little bit longer, let's say that it go up to 4, and I would try to do A plus B, it would start complaining, saying that matrix dimension must agree. These type of errors, you might, run somebody else's toolbox and get this type of error. So you already know that the reason is that the tool, the software, the function was expecting 2 things of the same length, but something went wrong somewhere. And then, this type of mathematical operation can't happen if we don't define whatever was missing. All right, then in Matlab, in the same page that I linked earlier, there are these operators that can basically work on an element by element, like we noticed here with the plus, but there are also these so-called matrix operators. Maybe not all of you went through linear algebra courses or that kind of stuff, But in general, the matrix operation, like a multiplication between the elements of two matrices of the same size, is kind of this formula. So you need to kind of sum, like you fix the row on one matrix and the column of the other matrix, and you do the multiplication of all the elements and sum them. Matrix multiplications and this matrix algebra is very useful in linear modeling and many other things. But often, at least in my experience, it's more often needed to work on a kind of element by element. So if you wanted to, multiply, let me make sure that B is the same in the example. Yeah, if you wanted to multiply the element of A and B one by one, using the kind of multiplication, the standard multiplication operator will throw an error. So if I would do this, it will throw an error because the inner matrix dimension must agree. So this is not the multiplication or the standard multiplication operator, but this is the matrix multiplication operator. So we would basically want to have two matrices of compatible sizes so that the so-called linear whatever algebra computation multiplication would work. If instead we need to work on an element by element, then the notation is with the dot. So A dot kind of times product B. And now, yes, and now if we look again, let me plot again A, B, and A times B. So now we see that, if A is this, first element is 1 times 1, it's a 1. 1 times 2, it's a 3, and 10 times 3, it's a 30. So now we did this element by element multiplication. Then, of course, it's nice to work with matrices. Now, magic, as we saw in the example, is just a way of getting a random matrix. It's not fully random in a sense that it's a matrix of integers so that the sum across rows and columns are the same. Just a funny way of having some matrix. So now we have a 3 times 3 matrix, and imagine that we would need to add, kind of shift the whole matrix of a value. So we saw this also in the example, but of course one could have a new matrix that is the same size, and in each row and in each cell of the matrix in its location would have the value that we want to add. But with Matlab, it's easy enough that if we just pass one number that we want to add or subtract to the whole matrix, that Matlab assumes that we want to add this number to all the elements in the matrix. So if I do this, now you see the numbers, they all increased of 100. Similarly, here in the next example here, I'm trying to add a row vector. So specifically, it's a row vector of the same size of the matrix, so with 3 columns. And then Matlab assumes that, all right, you are trying to kind of add this to kind of, to every line, to every row of the matrix. So if A was this, A plus the vector would be 10, 100, and 1000. And now we see that it did it for each row. So if the first column we had 8, 3, 4, it added 10 to all the elements of the first column, 18, 13, and 14. Now to kind of show you, it's not really what's behind the scenes because it's more efficient how Matlab does it, most likely their built-in function. But basically this is the equivalent of building a matrix from the vector so that the matrix is of the same size of the matrix they were trying to fit. So what if one wanted to do it in that way, to be kind of more explicit, then there is a function called repmat, which kind of repeats the vector or the array or the matrix that you're passing. So now with this repeat the matrix, repmat, it would take this input matrix and the repetition that we say, we are basically asking, repeat it 3 times in the row direction, and basically do not repeat it. Repeat it 1 time in it, leave it as it is in the column direction. So then with this here, I'm gonna enter it. I copy pasted it. So maybe I typed it. So they also have time to type it. So repmat, we have this vector of 10, 100, 1000. We want 3 times in the rows and the column can stay as they are, because then basically now we will end up with a 3 times 3 matrix. And yes, it is. So now we have a 3 times 3 matrix, which means that this rep mat, etc., if we sum it to A, like we did earlier, now we can get the same, the kind of the equivalent that we did here with this notation of A, matrix A plus the vector. And you can see that it's the same. So now we were just, with this rep mat, we were just more explicit that we really, wanted to repeat the matrix. Now, another operator that we didn't really come across is the transpose operator. Well, let's not go too much into the mathematics of matrix transposition, but kind of in practice, what it means is that you want to reshape, you want to make a row into a column. So if this is a row, let's type it 10, 100, 1000. So this is a row. If I would add this apostrophe, this single apostrophe at the end, it would kind of rotate, if you want to think it in a geometric sense, it would rotate the row so that it becomes a vector. So now, or it becomes a column. So now the same values that were forming a row, they're now forming a column. This is basically the same of, if I would have written it like this. So instead of the spaces, which means also command, we would have the semicolon. So then yes, it's the same thing. So now you understand that if we want to do A plus kind of, the transposed vector, which is now a column vector, now the addition will happen on the columns, so that every column of A will get, this vector added to each element. So you see that I also rewrite A for your convenience. So now with this operation, earlier we were adding 10 here, 100 here, and 1000 here. Now we're working across within one column. So we add 10 here, 100 here, and 1000 here, and we repeat the same. So that basically now that we didn't have a row vector, but we had the column vector, then the operation is kind of flipped, flipped in a sense, or transposed in a sense, that now it happens in the other direction. Compare this with the previous notation of 10, 100, 1000, where here you see the addition was going row by row. So basically then I wrote here also for kind of clarity, if this rep mat command was repeating the row so that we end up with 3 rows and the number of columns stays as it is in the vector. Now that we have a column vector, we would need to kind of do the opposite, that we don't need to repeat along the kind of first dimension, but we need to repeat in the other dimension. So that if I type rep mat 10, 100, 1000 with the apostrophe so that it's a column, then in the columns we don't need to repeat it because we already have, or in the row, sorry, we don't need to repeat it because we already happy with the 3 rows, but we only have 1 column and we want to have 3 columns. And here is basically the kind of matrix that would be added to A here to obtain that. So in my opinion, it's good to kind of, these are kind of the building blocks if you need to code something with MATLAB, meaning mathematically. Often, of course, we end up using toolboxes, whether they are given from other people or they come with MATLAB, so that often we might not actually need to do this type of sums and this type of, low-level operations. But in general, it's useful to be aware of these things, because even if you just need to read somebody else's code and make sure that the math under the hood is correct, you have kind of the knowledge that was there a typo that the dot product was actually product, or was the size of the matrices that are summed together correct? All right, let's check the HackMD if there's any question on this topic. There's no question, but basically the example that I've been using, they come from the page that I also linked there. So this is another, you can also, they're not exactly the same, but you can learn also with this web page. Now I'm listing here some useful matrices, because sometimes you might have seen this already, that sometimes we need to generate some data or we might need, you know, some quick way that we don't want to start manually typing all the numbers like we did here. So there are some functions that immediately create a matrix, and you can pass the size of the matrix. So zeros is one of those functions. Now zeros with one number will create a matrix, in this case 3 times 3 of zeros. If the size, you know, if it's not a square matrix and we would like to do a little bit different, let's say that it's 4 rows and 2 columns, then we pass 2 parameters. And now we have a zeros with 4 rows and 2 columns. Maybe we need to have it into a volume because we need to create an empty volume, you know, where we need to store our process data. And now let's do that it's 4 rows, 2 columns, and 3 kind of in the Z direction, three slices, if you want to think it. So this, you know, this would be slice 1, which is 4 times 2, slice 2, that is 4 times 2, and slice 3. So that together, you know, they would build this volume, this empty volume, because they're all zeros. There are other matrices, there are other functions that are convenient to generate this type of, you know, pre-existing or needed. So for example, this I in this case stands for identity. So if you're familiar with linear algebra, it's the identity matrix where there are zeros everywhere else and ones in the main diagonal. Then like zeros, we also have a matrix called ones, and it works in the same way that with one parameter, this will create a matrix that contains the number 1 in this case, it's a 2 times 2. And of course, we can also do it 4 rows and 2 columns. So that we would kind of, you know, basically fill the values, initialize kind of the matrix with all these, with all ones in this case. There's another special number in Matlab. That's not just that, there's a couple of special numbers in Matlab that we didn't really cover. And one case is the so-called not a number. So this not a number is like a way of telling Matlab that, you know, that for that point, we don't really have data. Because sometimes let's say that you collect data and 0 means actually 0. And for some, let's say on a certain day, you were not able to collect data. If you save it as a 0, maybe it's not correct, because it doesn't mean that on that day it would be collected as 0. So often, in some cases, we need to basically explicitly say that we are missing some data points. And so not a number is basically the Matlab way of saying this. And similarly, with all the other functions, we can create a matrix, in this case 5 times 5, initialized with not the numbers. So that, you know, we would kind of initialize our matrix and then we store what we need to store. Then we had a look at this magic, which is just a way of generating these funny matrices with this property. And then, of course, if you remember in the software carpentry, we looked at how to kind of take subparts of this matrix. Let's say that we wanted to take only the first 2 rows and 2 columns. So we did something like this. So from row 1 to 2 and column 1 to 2, and we get kind of, you know, the little corner in the top left of this matrix. But sometimes we need to take out from a matrix something that is a little bit more complex. Let's say all the values in the main diagonal. So there are functions for that. And diag is exactly this function. So that by writing it like this, instead of, it will basically return the elements in the diagonal of this matrix as a single vector. So now, you know, we extracted only what we needed to extract. We could have done it in other ways, but you can understand that then it would have required, you know, it's not as simple as we wrote it here with these indices. It would require maybe a for loop or something like that. For loops are never good in the sense that they slow things down, with MATLAB at least. And so it's more efficient to be aware of these kind of functions, you know, to extract what we need from a matrix, from an image, from whatever table. Another function that I mentioned here is the triangle with a U, so the upper triangle. So now the upper triangle will basically does what it says. It will return the so-called upper triangle of the matrix. So if the matrix is here, where I'm showing it with the mouse, the upper triangle matrix keeps the diagonal, but only returns the values on the top. And then similarly, there is also the lower triangle that would return. These are also useful in linear algebra, but also in other fields, like if you deal with matrices that are symmetric, like covariance matrices, the information is the same, so you can only look at the top triangle or the bottom triangle. Also at the bottom triangle here. Another way of looking at the matrix is with the top triangle in this case, without the main diagonal, so that we really keep only the top triangle. This is, for example, useful in covariance matrices where you know that the main diagonal, they're all ones, and so you just get the values from the top triangle. All right, so of course you can explore more of these matrix and math operations and useful matrices with the help, of course, so that you can get more info on these things. And there are more examples, especially this is actually the best way to learn this, maybe rather than going through the example, is to start looking at the computational code of whatever tool that you're using, so that you kind of go inside the code and see, do they initialize the output with all zeros because they know that the output will be 3 times 3, and so they prepare it like this, etc., etc. There are other operations with matrices. I listed these two because they are very common. So one is the flip. Let's first define a matrix that we can use as example. So the magic square, 4 times 4. So flip UD, it's not really a transpose like we saw earlier, but it will kind of flip the bottom rows with the top rows, so up, down. So now the flip up, down version of the matrix, you see now the 16 is here, and instead it was there, and the 2 is here, and instead it was there. So it's just flipped along kind of, the vertical dimension. And of course, we can do the same in the left-right sense. So that now if the 13 was here in the extreme right, now with flip left-right, it ends in the other side. The other thing that we saw earlier, so this is the original matrix A, was the transpose. The transpose would move this, whatever is in the top right corner, to the bottom left corner. So you see, so the flipping happens along the main diagonal. All right, so you can understand already that these are useful. For example, let's say you're doing signal processing and there are this type of signal processing where you need to flip time series or images if you do image processing. So this type of mathematical operation are useful. Something also very common if you look at the computational code written in matrix, also reshaping of matrix. The reason is that, well, I would say that the main reason is that sometimes, so now for example we have this matrix A. If you remember, when you write it like this, you just reshape the matrix into a single column. So now I press it, there will be all the numbers in this order, 16, 5, 9, 4. So always the columns are the more important, then 2, 11, 7, 14, etc. Let's see. Yes, so you see. Now, the reason to kind of reshape it into a single column is that there are often tools that they don't need to work, or they're not built to work with specific sizes of matrices, but that they operate kind of, how can I say, kind of in a univariate sense across all the cells. So then you can just reshape your matrix as a single vector and run whatever operation you need to be run, because it's more efficient to have it as a single vector. But then you need to reshape it back, so you need to kind of go back. So then the reshape command would kind of bring things back to the original. So if now the input that I'm passing here is this vector, is this single column with everything, if I reshape this back as a 4 times 4 image, now I get the original A once again. Or maybe I need to do some strange operation and I wanna, like in the example here, reshape it so that there are 2 rows and then there needs to be 8 columns, because then we need to have 16 elements. So now the original matrix is now reshaped into something different. Of course, this is field specific. You might never need to run these things if you don't really need to go down deeper in the coding. But at least even if you just read someone else's code, these are the types of functions that you might easily come across. All right, let's check if there's anything on the HackMD. Okay, there's no questions. So hopefully I'm going at the right pace for understanding these things. Another thing, if we finish with the kind of mathematics that we can do with Matlab, is of course complex numbers. Complex numbers are very useful for sure in signal processing, so they're not just in mathematics, because there's many signal processing functions and algorithms that requires complex number. So the way a complex number is defined in Matlab is that you would have the so-called imaginary part, which can be specified as j or also I. It's the same kind of. So if I define this number c equal to 1 plus 1 times j, so now I have a complex number that is written like this. So it has the real part and the imaginary part. We can look at the workspace and I see that c is still of the class double, but it has an attribute of being complex. So, it's not just a kind of a normal number, meaning a real number, but it has a imaginary part and a real part and an imaginary part, which we can of course extract like we would do when we in mathematics. So real of c will just return the real part, and imaginary part of c will return the imaginary part. In this case, they're exactly the same. So then here it's a little bit, because at least 2 or 3 people asked about signal processing. One of the most common things that you do with signal processing is running a so-called fast Fourier transform. This might not be relevant to all the people listening, but it's a kind of good example to understand what you can do with complex numbers. For those who are not familiar, basically Fourier analysis is a way to kind of, once you have a time series, you want to know, let's say, what is the frequency content. If this time series would only contain one sine wave, one frequency, then the Fourier transform would just show you kind of that frequency is present with strong power and everything else has a low power. Here I generated some random time series, so let's go command by command. So this rand n is the generation of random normally distributed numbers. Let's have a look at rand n. So here, it's kind of similar to the previous matrices that we saw, I and zeros, that if I type rand n of 2, it will be a 2 times 2 matrix of these random numbers, Gaussianly distributed random numbers. If I run the command again, I will get different numbers because they are random. They follow a random generator. Every time is different. Here specifically, I kind of ask Matlab to make a time series of random numbers of length 1024. So we want to have 1024. Let's do it like this to kind of decompose the command that I wrote here on the code. So now X contains a time series of random numbers. We can plot it, and yeah, it will look like something like this. It looks quite random. Of course, it's difficult to say that it looks quite random. Maybe there are other commands like histogram of X, so that does it look a little bit normally distributed. Well, actually, yeah, we were quite lucky here. It's not, fully symmetrical because we only are taking 1024 numbers. Maybe if we would have gotten a little bit more numbers, let's say that we add some threes. Well, let's not exaggerate, but let's say that we have 100,000 numbers here. So now X is really big, and maybe the histogram will look more, it looks more like it's still not the ideal perfect Gaussian distribution, but it's quite okay. But for this example, we are happy to get kind of just 1024 points. But then it's a bit kind of, if you work with signal processing, this kind of white noise, as they call it, it's a bit silly example because it's not that interesting. There's no, much content. So one way of kind of building a signal that looks interesting enough is so-called random walk, where you basically sum all the values. It's kind of the integral that, if you did a bit of calculus, it's kind of the sum of the first value. The second value will contain the previous sum, etc. So this is called the cumulative sum. Just to give you an idea that, let's imagine that we have a vector of numbers from 1 to 10. The cumulative sum of this vector would be 1, then 1 plus 2, then 1 plus 2 plus 3, 1 plus 2 plus 3 plus 4, and here it is. So here is 1, this is 1 plus 2, this is 1 plus 2 plus 3, this is 1 plus 2 plus 3 plus 4, so this is the cumulative sum. And so here I'm combining the cumulative sum with some random numbers so that we get the so-called random walk. Now let's then run it. Cumulative sum of random numbers, Gaussian distributed, 1024 rows, 1 column, close bracket, yes. So now we can plot X, and it's a signal that is a little bit more interesting than just a random noise. So, it has some slow growing and falling, but also some jumps. So this is the so-called random walk. If now this is just an X, if we would have a X and Y, this would be the equivalent of a random walk, where at every point kind of the direction of the walker is random, but then of course there is this kind of memory of where the person was walking. So now we created basically a time series that is a little bit more interesting than just some random noise. But of course, with FFT, now this time series has lots of, if I plot it again, it has lots of kind of, the average is a strong number. Now the FFT plot wouldn't look good with the very strong average, because the average in a time series is the zero frequency in frequency analysis. So what I'm doing here is so-called Z scoring, which this function removes the mean of the time series and scales it so that the variance is 1. And then we add a smaller mean just to make things interesting. So now let's also do this bit, Z score of X plus 1. Now if I plot it again, it will look very similar, but now the difference that we scaled it. So now, it has a mean of 1, and the scale is a little bit more, not going too much, not going too big. The reason is just, well, there are double reasons to kind of get a nicer looking FFT plot, but also for you to kind of see this type of functions that are often used in time series analysis. All right, then this capital X equal FFT of X, this would run this FFT operation. So now if we look at the workspace, capital X is a complex number. So now capital X has the same amount of numbers as the smaller x, but now if you are familiar, or if you will learn more about FFT, now these are frequencies. And specifically, what the FFT does is that now these are complex number. So then what I'm doing here next is that we can plot, for example, the real part and the imaginary part. So I type figure. That is a way to say, open a new image where I'm going to start doing things. and then plot the real part of the capital X, so that FF, the Fourier transform of the time series, and this is the real part. Doesn't looks a bit ugly, but that's how it is. And then the imaginary part. All right. So you notice that when I wrote plot imaginary part, I lost the plot of the real part. And you know, maybe I wanted to keep it. So I could have done it like this. I could have done it figure. And now I get a new figure. But now it's a bit of a mess. So now we add figure 1. I want a figure 1 to have the real part, but now it has the imaginary part. Now I have a figure 2 with nothing. How do we solve things? We can solve things. Instead of just typing figure, we can type figure with the number. So now we're telling Matlab, hey, please, can you just go to figure 1? And now we are kind of, the scope is figure 1. And now I can say, just give me the real part on figure 1. And now it's back, the real part. And then we tell Matlab, now I want, give me the scope of figure 2. And now we are in figure 2. And the command that I run here will not will not delete what's in figure 1, will now work in figure 2. So now I can plot the imaginary part of this Fourier transform in figure 2. So now I have the real part and the imaginary part. This is a little bit similar to what we did in the software carpentry with those figures that we were building there. But there we didn't really explain, you know, that we can actually pick which figure. The picking, of course, happens also graphically. So now that I click with the mouse on figure 1, now the scope is not anymore figure 2, but it's figure 1. So if I type title, where is this going to be? This is going to be on figure 1, because with the mouse I clicked on figure 1. If instead with the mouse I would click on figure 2, the title, this will end up in figure 2. And yes, it ended up there. So you see that kind of, you know, you can have multiple figures and you can recall different figures. Let's say that you forgot to add the label of the axis for figure 1, then you can just go again, give me figure 1, please, and add the axis X label. And these are frequencies because it's a Fourier transform. Frequencies. Frequency. All right. And now that, because we wrote figure 1, the scope went to figure 1 and the X label command was applied only to figure 1. I close everything now. There is another command, which is hold on. So now if we just type figure, Matlab will just give me the figure number, the next available. Right now I did close all. There's no figures open, so it will just give me 1. And yes, you see here that it's figure 1. So now we can do the plot of the real part of the Fourier transform. And then I can click, and then I can write hold on, meaning now don't delete what I just plotted. Keep it there, but overlap something else, the imaginary part of the Fourier transform. And now Matlab gave it a new color so that, you know, it's not mixing with the bottom one. So now in the same figure, I can see the real part and the imaginary part. And then with the zoom buttons, like I showed you earlier, if you have a more recent version of Matlab, they will be here. But with older version of Matlab, they're up there. Then you can start zooming a part of this Fourier transform, and, you know, and basically look at having a closer look at the data. Another thing that is useful is, you know, well, let's continue with the examples. So in signal processing, often looking at the real part and an imaginary part of a Fourier transform is not that informative. We often want to look at the magnitude. So for a complex number, the magnitude is like the distance from where the number is to the origin. So, you know, if C is our complex number and it has 1 as a real part and 1 as an imaginary part, so the distance from the origin will be, you know, kind of the diagonal of that square. So this is the square root of 2, basically. So now for the Fourier transform, it means that for every number at every frequency, instead of having a real part and imaginary part, we just want to have the magnitude. So specifically, let's open a new figure, and now we want to plot the magnitude, also or absolute value of these complex numbers. So now this looks more familiar as like a spectrogram, that you would basically look at the frequencies of this signal that we have invented. Now there's still some problem that the scales are really, they're really big, so that here it's it goes from 0 to really big numbers, but there's so much information here in this low scale that I'm not able to see it. So a way of dealing with this is to basically, instead of having a linear plot like we have right now, it's better to have a logarithmic plot. So if you remember what I said earlier, with this interactive way, you can actually select the the properties of the axis, and now I want specifically the y-axis, and instead of being in linear, I can pick log. So now I switched the axis. Instead of having the so-called linear order, now it has a logarithmic order. I could do the same with the x-axis, and here you already see that there's even the option for z-axis, but right now we don't have the third dimension. This is just a two-dimensional plot. We are happy with the linear scale in the x-axis. You need to scroll down a bit if you don't see it. But now it's much more clearer with having having a logarithmic y-axis, because then we can really see kind of the order of magnitude that in the slow frequencies, there's lots of energy in this time series, and in the highest frequency, the energy is really low. So now this would be kind of, they're not exactly decibels yet, but it's like looking at decibels for those who are doing signal processing. Of course, now this operation of picking the tool, clicking on the axis, changing the scale, it's not that, reproducible, because we need to do it manually. So there is a way of doing it by using semi-log y, which basically means in the plot that you're gonna do, please use a logarithmic scale for the y-axis. So now if I type figure and then semi-log y, the absolute value of the Fourier transform, now this is in logarithmic axis. Often you actually want to have a little grid to help you. So grid on, I can add it to the code and upload it later. Grid on will also kind of, make your life easier, so that you can, for example, see that the highest frequency have a power of whatever they have, and the smaller frequency are 3 or 4 orders of magnitude bigger. Okay, and this basically ends the part 2 and basically the second hour. But you can already see that I'm going more and more towards graphics, and the third part will all be about graphics and making figures. So the kind of order that I kept for this last lecture, if the first part was more like getting data, structuring the data, loading data, having data in the memory, this second part was more about crunching numbers, processing the data. The third part will be more about producing an output, which often means, producing images for your reports or papers or whatever you need to do. Let's first check if there's anything on HackMD. There's no questions. If you could just give me a thumb up if the speed is good, that I'm not going too fast like in the previous days. So you can just, if you click on these participants with Zoom, you can click on the yes if the speed is good, or there's other buttons like go slower, go faster. So I can see that there's 1, 2 thumbs up, 3 yes, and nobody's saying go slower, go faster. So at least 6 people have voted that the speed seems quite good. If you feel that I was going too fast, you can just say it. But I think now then it's a good moment for our 10 minutes break. And you can, of course, ask on Academy if you need some clarification on things that I show. And once again, I remind you that if you didn't already send me your name and surname for the credit or certificate, send me a chat message on Zoom with your name and surname so that I can mark you down. If you already did it, you don't need to send me a second message. So break until 14 sharp. Okay, now we have the last hour together. Thanks for quite impressed that almost everyone is here until the end. I remind you the HackMD link. If you click there and scroll down, you are able to anonymously type questions or comments or things. Feel free to also write things, that we might not be able to cover right now, but you might have an open question, that you are curious about Matlab. You can write it there, and at some point I can answer today or even later. The idea also would be to kind of keep this HackMD, since there's nothing personal here, keep this HackMD for like archive it and attach it to the video so that people can go back to this document if there's anything interesting here. All right, but then, so for the third part and final part, we cover a little bit more advanced topics when it comes to graphics. In this, so far we've been just playing with this plot command and sometimes with this image SC image scale command to just look at these plots. But already you got an idea in this interactive stuff that I was doing with this FFT that there's a little bit more, that we can add more things to, basically start building figures that are closely resembling what you see in scientific papers. There's many ways of making figures. Matlab is just one way of making figures. I think compared with other tools, that Matlab is actually quite good. That of course it might take some time to produce the perfect figure that you want, but Matlab is they have quite powerful set of tools to do most of the things that you need to, or at least most of the things that you see in scientific publications. So right, so let's clear all and close all so we don't have anything open. And now the first section that I'm going to cover, and of course you find the code in the Git repository. The first section is about the so-called line graphs, which is basically what we get when we call the plot command. So most of the examples are here in the link that I added in the code. I can open the link also just to quickly show you. So we are still under the kind of basics of Matlab documentation. And here, you have multiple kind of tutorials that guide you through these things. And I kind of picked few examples that are noteworthy, but you can go deeper into all these different types of plot depending on what you really need, what you need to do with your research or tasks. All right, so now let's start here. So the first thing, we need some data to plot. And now if you remember, this line space command is just a way of getting kind of linearly spaced numbers, basically 100 values. In this case, we wanted that they go from 0 to pi. Pi, is a constant. So that specifically, because we're planning to plot a sine wave, we basically want to cover the full period of a sine wave. And we want 100 kind of samples, 100 spots. So if you type along with me, now we created the X. Just, let's have a look at the X. I just not do plot X. And so as a reminder here, we have kind of all the indices of X. So the value at location 1, etc., up to 100. And here in the Y, now we have the kind of what is stored inside this vector that basically grow from 0 to pi times 2, which is basically 6 point something. If you do x of end, so the last value is 6.2, 6.28, which is basically 2 times pi. And pi is this constant that is already defined in Matlab. We don't have it in the workspace. All right, so we got the X, and of course we also need to get a Y. And here specifically, we want to look at the sine wave of X. So that basically this is just a mathematical function, the sin, the sinus. So that when we do plot X, and y, we would basically use the x scale, and for each of the element of x, we'll return the y. And now exactly what we were expecting. So here we have all the values, 100 values from 0 to 6.28, and the corresponding output of a sine. So of course we need to label our axis. So x label is gonna be x, and y label will be y, and the title, plot of the sine function. All right, all this is familiar to you. So already, as I briefly mentioned earlier, we might want to add things on top of this figure, because if I would just now type a new plot command, we would just lose everything that we have plotted. But often you see that people need to compare plots, need to compare time series, whatever they need to compare, and it gets really handy if the two things you want to compare, they are overlapping. So now the command hold on would basically say to the figure space, don't delete what you have there in the figure, don't delete anything, but just add on top. So we type hold on, we are here basically. And now we want to create a new y, which is y2, just the cosine of the same input. So now if we do plot, so the x range is the same as before, but now we want to plot y2, which is the value of the cosine. So now if we go back to the figure, now we see that yes, we got the sine wave in blue and the cosine in red, orange, whatever the color is. So now it's interesting that something that we didn't mention before, when we write the statement hold on, it's like they were switching on the option to hold, to keep the memory. But there's also an equivalent hold off. Hold off would basically switch off this hold, so that if now I would plot something, it would delete everything. Let's, for example, replot the sine wave. Now we will lose everything, but because I wrote hold off and we lost everything. And by everything, I really mean everything, even the labels, even the title. It's like a new figure. It's like forget everything that was done so far and start from scratch. All right, then this is kind of what is known so far. But what is interesting is that, of course, there are multiple ways of plotting these lines. So let's remake this linear space. Here specifically, we just want to have 50 values, 0 from 0 to 2 times pi using 50 values. And then y is the sine of x. And now we do plot x and y. And now this thing. So this thing here, it's an extra option for the plot function, which basically is describing the line plot. And specifically, this would mean give me, instead of plotting the figure as a continuous line that we saw earlier, plot it as a dotted line. So now if I press enter, now it's very tiny in the screen, but it's plotted as a dotted line. These type of properties, of course, you can also interactively change them with the mouse. So once you click that edit button, you can pick the figure. Now I clicked only once, then I click twice, and now I get all these extra options. So the line can be dotted or continuous, as we had earlier, or dash dash. It's like this dashed line, and these symbols that you see here, they're basically what you would pass in the code. This is dash dot line. So you can already see that now we could even increase a bit this thickness of the line. So instead of this 0.5 points, we could have it of 1 or 3, maybe this dotted line with a thickness of 3. Well, it's still not the most visible, but that's okay. I mean, you kind of got the idea that after in the plot command, after the data, so the x data and the y data, we can pass basically this type of options that we can get with the different that we can get with the line plot. There are many options, of course. So let's see if I'm, maybe I can actually go here. Let's see if I find, I know that there is a chart with all the options that are available. Line properties, here it is. Maybe I add this to the code also so that later you can, oh no, I already added to the code actually. All right, so it's the link that is there on the code. So that basically, like all these extra parameters that we can add to the plot command, they are summarized here for you. So for example, this is the default, the solid line, the dash dash would be the dash line, this column would be the dotted line that we were using, etc. There are other things that are, for example, useful, like colors. So now let's try some colors. Sorry, I lost my Matlab. Here it is. So let's close all, get a new figure, and now we do again plot X and Y. And we want to say that I want it in red this time. The default would be blue. If I don't write anything, it's the blue. Now it's in red. I don't like red, actually. I should have used black. In the short, the nickname for black is K. So now it's a black line. And here in this page that I linked, I'm also pasting it for you in the chat for your convenience. So this page kind of shows you already kind of these pre-coded colors that are available as a short name, as a nickname. Then there are other things that we can do. And for example, and a very important thing that you often see in papers is the markers. So the idea of the marker is that, when we do a plot, let's go back to math. When we do this type of plot, so this is a continuous line, we're not actually able to look at the data because in reality, we know that this is not an infinite, line that at some point, in this line was built using only 50 data points. So sometimes it's useful to actually show the data points. Let's do another example. Let's imagine that our data point, they still go from 0 to 2 times pi, but instead of having 50, we only have, let's say 20, all right? So now the amount of x points is much smaller, and then y is the sign of x. So now if I do a plot of x and y, now you see that because we have less points, things are starting to get a little bit more rough. I zoom in, so now because we have less data points, what Matlab is doing with the line plot is just connecting the dots. Before we had more data points and we had a smoother line, now we have less, we're kind of downsampling our data. So the point here is that sometimes it's useful to actually show the data points. And there are the so-called markers, the plot markers. So now in this extra option, I'm adding a star, for example, so that instead of plotting the plot as a line, it would just plot it as stars. And now, now I really see the points that I have. So in this specific moment, I only ask for 20 points of X and the corresponding 20 in the Y. And these are what we got. So the plot, of course, it's useful to maybe have also the continuous lines. So we can combine markers, or the marker for the points and the type of, marker or the type of line. So now we would want to have continuous line and the marker as a star. And now we combine the two things. Or maybe we want to have continuous, like instead of having continuous line, dotted line and the star. You don't like stars, or you have another figure. Let's do another figure. Let's hold on. And y2 was the cosine of x. And now maybe we want to do the cosine plotted, then instead of stars, we can pick another marker. So from the same page, on the marker, we can have circles, we can have pluses, small dots, axes. Let's say that we like these circles. So now in the cosine, I want to plot them circles and dotted line. And of course, I put the hold switch to on so that I don't lose everything. And now I can run the plot command. And now the cosine has a different color because Matlab kind of automatically picks the color if I don't force the color. But now it uses the dots instead of the whatever stars that we had earlier. But of course, we can also add the color in the same command. Maybe we didn't really want to have this color automatically picked by Matlab. Maybe we want everything to be black. And so I can add the K in the same string. I can also add the K, which was the nickname for the black. And now that line is black. And maybe I can go back a little bit in the history and make sure that also the other one is black. So now everything is black, but you see often this in plots that this would be the equivalent of a black and white figure, but you are able to reference to the different curves because one has the markers in with stars and the other one has a marker in with dots. So this is something that you see commonly in this black and white version of the figures. Okay, if we go back to the code, well, I improvised a little bit more, but basically here the example was the same. So specifically the cosine was a combination of this. This is the marker for this dash dash line, red, and the marker would have been these circles. And then you can explore here from this page other properties. You can actually change the size of the markers, for example. So maybe I'll show an example. So close all. Let's do a plot again, like this. So this would be, well, let's also have a continuous line. But then the markers are too small, right? So let's have a bigger marker. So then these properties that are listed in the page from the link, marker size, all close to the other, you can pass it as another parameter. So marker size becomes a parameter. And now maybe let's give a big number just for fun, 20. All right, now we made the stars, we made them really big. So that now, it's really clear with my image. I'm gonna put this also in the code so that you will have it later when I push the changes. But the same would go for all the other properties that you see here. So marker indices, marker mode, and you can explore all the properties that you can change. And of course, the same properties, as I said earlier, you can also change them with the interactively with the tool here. I double click the plot. And here, basically, you see the marker size 20. We set this to 20. I think the default value is something around like 6. Yeah, looks like 50. So this is more Christmassy. All right, so these are the very basics of the plot command. And as you already feel, these are useful because you see this type of plots in the literature, in the papers that you read or that you publish. Then, of course, all these properties. So I showed you the web page that gives you the list of the properties. I show you how to get the properties with this interactive tool with the mouse. But sometimes we want to access these properties programmatically from the code. So let's do a nice clear all to start fresh, close all to make sure there's no figures. So let's define again a linear space that goes from 0 to 2 times pi. This time we're happy with 25 samples. And then y is still the sine function. All right, now the plot command. It's not just the plot as we showed earlier. It also has an output parameter. Let's call it ln, like a short nickname for line. So plot x and y. This will just do the normal plot as we saw earlier. But now ln is a new object, is a line object. So if I look at if you look at your workspace, now ln is a type of, the type is Matlab graphics chart. It's all very nested things because this comes from the so-called object-oriented programming that is coded, that this line is a child of whatever other classes are on top of it. But basically now this object, this variable ln that we have in our workspace, contains all these details that, how can I say, about the plot. And I'm literally saying everything. So now just by working with this ln, I could start changing, the line style, the marker size. So I could start doing, for example, maybe one thing that I should explain, this is not a struct, but this is a specific class. If this would be a struct, you would type something like ln dot marker, right? If you remember the struct. But in this case, this case actually works. It didn't used to work. But normally with things who are not struct, who are classes, you use the set and the get. So get variable ln property marker, and it's none, and then set variable ln property marker, and we want to set it to star. All right, so now I'm going to add this to the code also. You can type it as well with get. With get, you get a property from the so-called plot handle. With set, you set a new value to that property. So now, for example, I set the marker to be the star. And if we go back to the plot, yes, now the marker is star. Then I can look again at ln, and maybe marker size, I'm not happy with it, so I could do set for ln, the marker size parameter, let's make it 20. So, but basically, with calling multiple times these settings, I can actually programmatically change all these properties from the plot. There are many properties. Here's Matlab is telling you show all properties. So I'm going to click here, and this is all that is kind of stored about this plot. Some things are empty. For example, there's no, I don't know. Well, right now, I mean, some values are not there because we didn't add them, but eventually, you can start, let's say this marker face color or edge color, Now, of course, we don't have time to go through all these properties and see how to get things more advanced, but you at least know where to start if you want to, create your ideal plot. All right, then something that was requested by a couple of you was kind of working with 2D and more specifically with 3D images. So Matlab actually comes with some data sets that you can use as an example. One data set is called MRI. So it means that you don't need to download anything. There's already some MRI.mat stored somewhere in Matlab. And that MRI.mat specifically contains a magnetic resonance image of a head. If you're curious and want to know where this is stored, it's there. So it's MRI.mat, and it's part of the demos, of the Matlab demos. All right, so let's clear the workspace and close all so that we can start fresh. I'm in this part, section 3 of this example. If you downloaded the code, I don't have anything in my workspace. So if I would just type load and this MRI, by not typing anything, this is the equivalent of doing MRI, of typing MRI.mat. All right, so now I have 3 variables in my workspace, similar to kind of what we did earlier with the dog and the cat, but it's not convenient. I'd rather have, have them all together in a struct. So I prefer type it like this, that I'm gonna have a struct called MRI, where I'm gonna load this MRI.mat from the Matlab demos. Okay, now I have a struct that contains D, which is the data, the map, which is so-called color map, and the size, that kind of, the dimensions of this data. So now something interesting is that I would have expected this to be a volume, meaning that this should be, according to the example, this should be a volume of a brain image, so it should be three-dimensional. But in this specific case, I'm not sure why. There is, basically the slices, the so-called slices of this MRI image are stored in the 4-dimension. So because the example that I'm trying to tell you here is about 3D images, I'm going to squeeze out the dimension that is basically redundant, because basically this would mean that there is no data in that dimension if the size there is 1. So with this squeeze command, you would kind of get rid of this 3rd dimension that is empty, and instead just make a volume out of this 4-dimensional. So now if I run this command, let's type it so that you have time to type it. MRI data equal MRI.data. So I'm creating a new field in the struct equal to squeeze, which is this function to get rid of redundant dimension, and the original data is in MRI.d. All right, so now if I look at the struct, now we have the data, the new field actually kind of, is a volume, is a 3-dimensional image. So now MRIs, if you are familiar with MRIs, you already know, but you can guess already that these are basically images that are like 2-dimensional images. There are 128 pixels, and there's 27 of them, so that they cover the whole head of a person that is inside the MRI scanner. So for example, in what I write here is that let's have a look at the image at the so-called slice number 12. So we can type figure, image scaled, and now we call it MRI.data. Show me all the X values, show me all the Y values, and specifically I want the slice number 12. Now I press enter, and now this is the image. So now the color map for this image is the default color map of Matlab. If you remember from last week, we could type the command color bar so that we would actually kind of get a mapping of these colors. But often MRIs, for example, are plotted as a grayscale, so black and white. So I could change the color map into something else. Matlab has some predefined color maps, like a gray. If you type help color map, you can get more info on basically types of color maps that are available for Matlab. Here in general, you can type color map. And now this is the online help for the color map. And you see, for example, that the data is the same, but just the color map is different. Kind of, it's, one doesn't really need to explore and spend lots of time to find the ideal color map. But in general, so these are all the, now I was saying color map gray, so the grayscale, but maybe your field, I don't know, the convention your field is to have MRI images with this color map, let's say HSV color map. So if I would have written color map HSV, this would have been, not very useful with this image, but depending on your field, you can change the color map of the image. I'm happy with the gray. All right, so we basically looked at the kind of 2-dimensional image, but of course we were just looking at one slice number 12. If I would change the number, the image would change. Slice number 14. Now I'm increasing the numbers one after the other, and we're kind of going up through the whole brain, or until whatever is the final number. I don't remember. Was it 27? So basically all these slices put all on top of each other, they're forming a volume. And there are multiple ways of plotting volumes with Matlab. One way that I find quite handy is the so-called isosurface. So now this is a bit complicated if you're not familiar with 3D graphics, but it's not too difficult to understand. So the idea is that if we think of this volume, let's say this is a brain and there's other tissues. Let's say that this white thick one, around the brain is most likely the skull. So you understand that the intensity of the image, let's say around the skull or skin, whatever is there, the skull is actually this. This would be more the skin and the muscles. It's quite different than the intensity that you have inside the image. So one could basically kind of segment, as they say, the image, so that you say, okay, give me all the intensities that are really bright, for example, this skin and image of the head, and keep them all together, like find a contiguous surface so that, I end up with the surface of this image. This is exactly what happens, what this isosurface command does here. So in this next command, I type figure and then I type isosurface. So iso is comes from Greek, I think, if I remember correctly, which is kind of saying find the same. So find the surface so that you keep all the values. The data is this volume MRI data, and the values that we want to keep is an intensity of value 20. You can explore different intensities. So now if I press this, now we have a 3-dimensional plot. So now isosurface is one of those commands that instead of plotting 2-dimensional things like we've been seeing before with plot and images, now we have a 3-dimensional plot. And specifically, as you can see, it's a section that covers most of the brain of this person that was scanned. To add a bit of, I always like to have grid on so that one can actually see. And specifically here, this intensity of value 20 relates to kind of this skin and muscle. So kind of, it's brighter than the other bits. Even though, of course, inside there might be other pixels, or as they call them, voxels, that have an intensity of 20. And then with the tools here above, if you have a newer version of Matlab, they're here. There's one tool that looks like a spinning circle, and that is interactively 3-dimensionally spin, this image. So you can actually basically, now I'm looking kind of from the bottom, from where the neck would be, and here I'm going to look at it from the top of the head. So you can see what I was saying earlier, that there are some other pixels or voxels that have that intensity of 20, but basically we were able to here plot most of the head. I could try another intensity, something smaller, so a little bit more gray. I don't know if this is going to be nice. Well, didn't really change much, but now there's two things overlapped. Now let's try something bigger, an intensity of, let's say, 40. I don't know what to expect here. Okay, now I started to add more things inside the brain. I could zoom in inside the brain. I don't want to slow down my computer, but you basically get the idea that you can start exploring. It's not the prettiest MRI image, that the quality is quite low. This image would need some smoothing so that you wouldn't see all these kind of cubes, triangles, whatever they're called, polygons. but you get the idea. And you can already see that with this 3D rendering, if you're familiar with 3D rendering, there's a light that reflects, So all these parameters, they can actually be set if you want to change the light, if you want to add more lights or cameras, you can do all this fancy 3D graphics also with Matlab. All right. So I make sure that the most up-to-date version is on the repository. In the meantime, let's check if there's any comment on HackMD. There are no questions or comments. Okay. Now it's the final part. It's part 4, and this comes from the source that I linked here. And here the idea is that we can actually, kind of going a little bit more advanced with the plots, so that we can combine together in the same line plot more information. Specifically, we can have two y-axes, one for the left and one for the right. So let's clear all and close all so that we can start fresh. So now we will have a figure. What do we need here? We need an x that is a linear space from 0 to 25. If I don't have the third part parameters, this will mean that there's 100 values. Then we have y as the sign of these values divided by 2. They decided this, why not? And now there's an extra command before the plot. So now I'm going to say that the y-axis of this plot should be the left one, which is kind of, the default option. So that y-axis left. And now when we actually can call plot, we see that we see something a little bit different. And now plot as a y-axis of the same color of the plot that we made. Because we picked the y-axis left, it's on the left side. Matlab already has prepared a y-axis of a different color on the other side, but now the range is still the same because we still don't have a second plot that would kind of be related to the other axis. So let's add the second plot. And here, for example, they create another function that this is the square. So the square of all the values inside x divided by 2. Notice that what happens here, that it's not 2 divided by 2, that kind of the order of operation is this, that first you square every element and then the squared elements, they are divided by 2. So in a way it's better to always be explicit to make the code more readable, even though the machine is able to read it, but it's good to add these brackets for the humans. So now we have these R values, and now we say that the y-axis for this value should be the one on the right. So y-axis right. And now when we plot this new function R, so now you see, now the range is different. Now Matlab scale things so that they can all fit nicely into the same picture. But the blue plot, the sine wave, goes from -1 to 1, and this parabolic, whatever polynomial square, kind of goes from 0 to 300 and something. So the range is different, but of course it's convenient sometimes to have, as I was saying earlier, to overlap multiple plots so that you can infer, some, or you can show better your results. The same story, of course, is also for the labels. So this is similar to the scope earlier. If the scope earlier, I was saying that by typing figure 1, for example, I cannot tell Matlab, I'm going to work on figure 1. Now, again, I can tell Matlab, give me the scope of the left axis, because now I want to label things for the left stuff. So again, I type y-axis left, and now I can do some title. Plot with different scales. X label is the same for both axes, values from 0 to 25. But the Y label, now this will be affected. Now the Y label, this will depend on this y-axis left. So the Y label, this is the sign function. And now you see it's only here and it's color coded. Now I could do the same. We can do the same for the right side. So y-axis right, and the Y label here, right side. And here it is. So the y-axis have different labels because they correspond to different type of data. So then here in the following commands, it's just adding more to the, with hold on, we can start adding more things. What is interesting to notice is that normally when we hold on, we start getting different colors, but here the color starts to be meaningful, or it's not they are meaningful, meaning that now everything that is coded, that is color coded in blue, is for the left axis, and everything that is coded in red is for the y-axis. So then with the hold on, things start to be different than normally. So when I put hold on and the y-axis is the left one, now we want to add some more plots, so and more sine waves with different periods. This is y2, and we add y2, and now you see what happens is that the color stayed the same, but then Matlab automatically picks a different line style, so that we can separate, we can distinguish between the first one that we plotted and the second one. Then we can plot a third sine wave with another period, x divided by 4, and now plot x and y3. And here Matlab picked another plot. I don't know how visible it is through Zoom, but these are basically, it's a dotted line. And of course the same, the same thing on the other side. Now what Matlab is doing here, or in the example that we have here, now we go back to or we switch to this right side, right axis of the y-axis, and now we are loading some existing data. Let's load this count.dat. So these are one of those demo data sets that come with Matlab. If you just are curious, so this count, it's 24. I don't specifically remember what are they counting here, but there's some 24 values, and for each value, for each row, we have 3 columns. So we can compute some mean like we did in the carpentry code and standard deviations for this data. So these are the same that we noticed in the carpentry code. So let's compute the mean of this count data across the second dimension, which means that now if we look at our workspace, M has 24 values. So the mean was done across these 3 columns. The same can be done for the standard error, standard deviation, count the standard deviation to specify the dimension. If you remember from the software carpentry, we wanted this, that this second parameter was some sort of normalization option, with 1 being the default value. And now here, once again, if I check the workspace, so E and M are 24 values. And now we can plot, we can plot this error bar basically at the location, at the main location, we want to plot these error bars, these standard errors. So let's see how it looks, and it looks like this. So now Matlab added this extra plot using the range of the y-axis right that we put before. And in this specific case, it's a bit of a more complex example. Now, if you're curious to know what this error bar does, you can type help error bar. So it's another type of plot that basically does this. I think it plots the standard error of the mean, if I'm not wrong, but you can read the specifics. Like this is not the reason. And then once you're done, hold off, and you have your picture that contains lots of information. And maybe this is the main result of your paper. All right, so there's still some 15 minutes left that I thought it's good for, well, asking for feedback, of course, but also keep it open if you have any wish or any question. So let's switch to the HackMD. There's no questions. So before we separate, I'm gonna ask you for feedback about today and about the whole course. Write something positive and something that could be improved. Feedback is very important because, well, now for sure, I mean, for you, maybe it's not important anymore because you will not need to take this again. I pasted the HackMD link, but you can at least improve or give some feedback for the future generation. This is the, was it third or fourth year that we're doing this course, and we're trying to improve it and improve it a little bit more. So yeah, write any feedback. It's, I see that there's 5 people on the HackMD and there's 22 in the room. So I think it's, even if you don't have any feedback, click on the HackMD link and just scroll down and write, yes, everything is good, like I can't really extrapolate from those who don't write anything. Does it mean that you hated everything or that everything was amazing? So if you can just click on the HackMD, scroll to the end and write anything, that's good enough, so that your voice is heard and your message will be passed to future generations. If you can't think of anything to say, just say hi. But at least I know that you had a chance to express your opinion. We're not gonna, this is a bit different than standard. I mean, you still get a credit like any other course, but we wanted to keep things simple, so we don't have this my courses interface. I can actually stop the streaming, or not the streaming, the recording.